So, this is another frequently asked problem in coding interviews that test your understanding about arrays, dynamic programming, and also a little bit about two-pointer techniques, if it's about that approach particularly. So, hey everyone, welcome back to our classes. Today we'll be solving one of the most famous coding interview problems, tripping rain water. The problem challenges you to think about arrays and water collection and can be solved using variety of approaches. So let's dive into the problem. So the problem is pretty simple. It goes like this. You are given an array of height where each element represents the height of the bar at index I. The task is to compute how much water can be trapped after it rains. So example, you have a height 0, 1, 0, 2, 1, 1, 2, 3, and this is like the just random array, right? And your output is 6. So after it rains, 6 units of water are trapped between the bars. So that is your particular output, right? Because, okay, let's just imagine that you have several vertical bars of different heights placed next to each other. The spaces between these bars can collect rainwater. When it rains, your task is to figure out how much rainwater can be trapped between these bars after it rains. So, for example, I've already told you've been given an array, and you can see as an example. So, if you were to just create a representation of it, how would it look like? So, let me just show you. So, this is the pictorial representation, or let's just say a line representation bar, whatever you call it. It's just a representation of how it would look like if you were to just create a visualization of the problem. So here the spaces between the bars can trap water. In this example, 6 units of water can be stored between these bars after it rains. So the goal is to calculate the total amount of water trapped between the bars. In this case, the output is 6. So if it was a little bit different, how would it have been done? Or what is the optimal approach of solving this problem? How we can possibly solve this problem? How we can come up with the answer that how many units of water can be stored between these bars? So there are three ways of solving this problem. A brute force approach, then there is an optimized approach using extra space, and then there is the two-pointer technique. So today we'll be working with the extra space. We're not going to go into the two-pointer. We'll just look at we'll just take a brief overview of two-pointer technique and also the brute force approach, but we're going to do specifically the coding for extra space. So let's just first understand all of these things and study the pseudocodes and see which one is more optimal for solving this particular algorithm or problem. Let's just see. The first one, brute force approach. So in the brute force approach, we can calculate the water trapped at the index I by finding the maximum height to the left and right of that index. The water trapped at index I is the minimum of those height 2 minus the height at I. So the steps are pretty simple. You have to just perform 3 steps, right? For each bar, find the maximum height of the bar to the left, and then you have to do the same to the right. Okay, done. Then the water trapped between each bar is minimum of 2 heights minus the height of the current bar. That's the basis of solving this algorithm. So right now you can see on your screen, this is the pseudocode of how you can possibly solve the entire equation or the problem, let's just say. But is it optimal? Most of the time the brute force approaches are not optimal because it has time complexity issues, O n square, and due to the nested loops that we are using up here. So we can optimize this using the extra space, but before that we'll just take a brief look at another one, which is the two-pointer technique. Then we'll move on to our optimal approach. So the two-pointer technique, we can reduce the time complexity O of 1 by using the two-pointer technique. Instead of using extra arrays to store left and right max values, we can calculate them on a fly while maintaining two pointers left and right. So the steps are pretty simple. You have to perform 4-step process, use two pointers left and right starting at two ends of the array. Then you have to keep the track of maximum values seen so far from the left, which is left max in our case, and then the right. which is right max again. And then at each step, move the pointer that points to the short bar inwards. All right. And then you have to check if the height of the left is greater than the height of right. If not, then we don't care. But if it is, if the height of the right bar is bigger, then calculate water trapped at left using the left max. Otherwise, we can calculate the water trapped at right using right max. Right? It goes simple. So right now you can see the pseudocode. You can just pause and take a screenshot or something like that if you want to perform this. So now let's just talk about our optimized way of countering this question, the extra space. So to optimize, we can pre-compute the maximum heights to the left and right of each bar, reducing the overall time complexity to O(n). We'll store all these maximums in two different arrays, the left max and the right max. So this is a three-step process. We have to pre-compute the left max array, where each element left max of I stores the maximum height of left up to index I. Then we are going to do the same thing for the right side. Pre-compute the right max array, where each element right max I stores the maximum height from right up to index I. Then we are going to calculate the trapped water using pre-computed arrays. So now let's just do the coding. It's getting boring if you were to talk about a lot of theory. It's gonna get boring at some point. So let's just do the coding and understand how it's going. All right. So the first thing that we do is create an example input. As we have seen in our problem statement, we are going to do the exact same thing up here. Then we'll create a function calling it the trap. If not height, then return 0. That's it. Simple as that. If we do not have any kinds of height or something, then we're gonna simply return 0. But if we do, then we're gonna check the length of the height, and then we're going to create two arrays. Then initialize the water trapped as 0. Then we'll start to fill the left max array. All right, so we'll start to fill the left max array. It's pretty simple. Left max of 0, height of 0, and then we're gonna use a loop up here, which will give us the maximum of left max of I minus 1 and height of I. This is gonna give us the maximum of both of them. So we're gonna get which is max, and whoever is max is going to be the left max of I. Then the exact same thing goes. Okay, guess I've done something creepy. Okay, perfect. Then the exact same thing goes for the right fill. We're going to do the exact same thing, the right max. So the filling process is a little bit different for the right one, because in here we're going to do n minus 1, height also n minus 1, and the loop will be also the different. For I in range, n minus 2 comma minus 1 minus 1. Then let's just do the exact same thing. The right max of I is equal to max of right max of I plus 1 comma height of I. Right, done. So calculate water trapped. So water trapped can be calculated using a simple for loop. Not too complicated, just a simple for loop. Okay, it's perfect. Height of I. That's it. Damn straight. Then return the water trapped. Guess it's perfect. Does not take a lot of time to get done. So sort of trap of water, then the print the result. That's it. We'll be done with the entire example in just a few short seconds. And as you can see, water trapped equals to 10. All right, so we're done. Now just don't confuse yourself thinking that, okay, in example question we had output as 6 and now we have output as 10. That was an example output. I just wrote that down. I thought maybe I just thought in my brain whilst doing the paper coding, I thought that the answer was supposed to be 6, but it is 10. Alright, so that wraps up for today's video on tripping rainwater problem. We have covered 3 approaches: the brute force approach, the optimized solution with extra space, and the pointer technique. So remember, the practice is the key to master these techniques. Make sure you like, comment, and subscribe to our class classes for more algorithms and solutions like this. See you in the next one.